So welcome to today's discussion about normal shocks. In looking at the trajectory of the course, we're going to be looking at various flow features, starting with normal shocks and oblique shocks and expansion waves. And this is going to be, we're going to then combine all that information together, look at specific scenarios, inlets, outlets, lifting surfaces. And so this is the basic building block. How we approach this problem is going to be pretty similar how we approach all problems. Essentially, we're going to be appealing to conservation principles applied to a small control volume. This is going to be the running theme: conservation of mass, conservation of momentum, conservation of energy. Now, normal shocks are quite interesting in the sense that they're quite a special case, and they are the case where we have a flow structure which is moving forward in time, and relative to that, obviously, if we have fluid particles in this vicinity, then they move relative to the surface, the shock, which we'll discuss a bit more detail. They move perpendicularly. So the angle between the streamline and the shock itself, these are streamlines relative to the shock itself, streamline. That angle zeta is 90 degrees, and that's why it's called a normal shock. This figure here shows a Schlieren, really short Schlieren image of a shadow graph, because it's light and dark, of a gun being fired, and obviously you can see the someone's hand is here, the gun is there, the nozzle's just ejected the bullet or the projectile, and that projectile in this case is moving supersonically. We know this because there's a series of shocks coming off here, and the initial blast itself generates a shock wave, a spherical shock wave, and you see this shock wave move out radially. And this is a nice illustration of the various processes that are occurring, and as this spherical shock grows in time, it starts to slow down. Now, relative to that shock, the flow tends to look like a normal shock. So normal shock analysis is actually used to look at this example. This example is important. It's used for, or this analysis, which is on your first tutorial sheet, is for spherical shock, is important because it's used for safety cases for storing munitions. a blast wave grows with time, and that leads to an overpressure, which is bigger than ambient, significantly bigger than ambient, and that overpressure has a potential to knock walls off or break surfaces. It's a bit worse than that, because once it's reflected, there's like most things, there's an amplification of the pressure close to rigid surfaces, which means that they have a great potential for enhancing damage. The overpressure required for breaking things like windows is very, very small. You only need an overpressure for 5 kPa, and that's sufficient to blow out easily windows. In this particular case, we have our normal shock, something that appears as a normal shock here. And over here, we see our projectile. We see what we're going to look at later in lecture 2, an oblique shock. So relative to that bullet's moving along. Let's draw a little picture of it over here. Discuss it later on, a little bit more about what this involves. But relative to the bullet's moving on. If we're looking at the frame of reference, the streamlines will look like this. Because the streamlines have an angle zeta, which is quite different and well, certainly less than 90 degrees, then this is an example of oblique shock. We're going to focus on normal shocks, and the analysis is very similar, related. So to analyse this, we're going to kind of simplify this problem. So normally, in many cases, this shock wave is moving with high speed. We're going to get to an idea of how high that is soon. And in order to simplify this, we want to make the analysis simpler. We're going to jump in the frame of reference of the shock. And in that frame of reference, the flow is assumed to be steady. So I think in this particular case, this here, we have the shock moving right to left. So in the frame of the shock, the streamlines are bringing fluid through the shock itself. And we're going to denote the left hand to be region 1, the right hand to be region 2. And associated with region 1, we're going to have a velocity U1, pressure P1, density ρ1, and a Mach number M1. Just recap from our definitions of Mach number. Mach number is local speed divided by speed of sound. And so in this particular case, that's U1 over gamma RT 1 to the half. And what is the purpose of this calculation? The purpose of the calculation is to know the relationship between the left-hand side and the right-hand side. And what we're probably going to understand when we do this is that it's going to be probably in a relationship expressed in dimensionless form. So what we're aiming to do is to try and find out, in some sense, how M2 depends on M1. And in doing so, we're going to invoke a couple of fundamental principles, the notion that entropy must increase, and this is going to put some serious constraints on the type of solution that may exist. Now, in order to tackle this problem, obviously we've got our principles of momentum, mass, and energy, which will apply. And because we're going to apply them in an integral form, various elements to this problem tend to not to become important, and we're going to also take what we call an inviscid approach. Viscous effects play a very, very weak role in this. An integral analysis will not take into account very much won't take into account the thickness of the interface itself. And so the analysis itself is really based on looking at flow processes that occur in a control volume that overlap the shock control volume. Now, one of the features that we saw on the previous picture, and we've seen when we've had a look at these types of things, is that the properties of the flow on either side of the shock tend to be quite uniform. And so we're going to take that assumption that those flow properties U1, P1, ρ1 are essentially constant on the left and constant on the right, and that's a pretty good assumption. These shocks tend to be quite very localized. So the conservation principles, as we've discussed before, can be written in a vector form. It's a shorthand. But as we've discussed when we look at other types of problems, you've got, if you like, the mathematical form, which kind of, if we would say, kind of the full vector form. You set to a scalar form. Now, if you're not familiar with writing these out, and there's not an expectation that you'll be very so familiar, but there is an expectation that you understand the physical meaning of these terms. And so what we tend to do in many of these problems is to kind of use a word equation. So conservation of mass essentially means what goes in goes out. And in this particular form, for steady flows, it means the divergence of the density weighted velocity is 0. Conservation of momentum for the steady flows means that the force on the parcel of fluid is determined by gradients of pressure. Conservation of energy essentially say the change in the sum of the internal energy plus the kinetic energy is determined by the action of the work done by the by pressure on the flow itself, div pu minus div pu. So we take these equations and we apply them to a control volume, and because the gradients on the left hand side tend to be 0 and the gradients on the right hand side to be 0, it's those differences across that interface important. So the gradient of P is obviously 0 everywhere, apart from on the interface, and P2 minus P1 is not equal to 0. So there's a pressure differential, but the gradients on. So when we integrate this, what we end up with is a set of scalars relating left hand side and right hand side. Conservation of principles in the vector form essentially reduced down to this scalar form, and we've got our conservation of mass, conservation of momentum, conservation of energy. So conservation of mass, density times velocity is constant, pretty straightforward. Conservation of momentum, sum of momentum flux plus pressure is constant. Energy, sum of internal energy plus kinetic energy is conserved, and equation of state for an ideal gas. The strength of the shock is defined as the ratio of the pressures, so we're looking at a case where the shock is quite strong. There are a couple of things about this. There are these two cases of a weak shock. And a strong shock, which we'll discuss. So in this slide we're going to discuss frames of reference. This is a subtle thing for fluid mechanics and usually a more complicated element. So we're going to show the difference between what we call a laboratory frame, that is the frame in which the observer is stationary and the fluid processes move past them, and the shock frame in which you're sitting on the shock and things are moving relative to the shock. And the reason we need to switch from one frame to another is actually one frame of reference, which is the shock frame reference, is easy to analyse because the flow itself and the properties are steady. This would be steady. This is unsteady. You can analyse both of these, but it's just the steady case is a little bit more straightforward. So if we imagine this case of a shock propagating along a pipe, and this could be either through a valve closing, generated compressive shock moving upstream, a flame in a pipe, then what we have is we have a shock moving left to right, and upstream we have our stationary fluid because the flow signature hasn't arrived, it's supersonic and it's upstream. And let's assume that that shock is moving with speed u. Downstream the fluid elements will be moving towards the shock, not at the same speed, certainly at a slower speed, and the streamlines on the left hand side would be then all connected and terminate at the shock itself. Upstream there are no streamlines because the fluid is not moving. If we look at the flow in the shock frame of reference and we're sitting on the shock itself, what we notice is the fluid elements are moving towards the shock. So if we're in the shock frame, the fluid elements are moving towards the shock, and therefore the streamlines now move towards the shock, pass through the shock and go to the other side. Now upstream, those fluid elements are moving with the speed of the shock, u, and downstream the frame, with the frame of reference now moving left to right, means that the relative speed in region 2 is now big U minus little u being the speed of the flow after the shock in the laboratory frame of reference. In this particular case, our region 1, that the region is upstream, the region that then flows to the shock itself, and then that region downstream is our region 2. So we relate and the aim of the calculation is then to relate what goes upstream to what goes downstream. But it's subtle and needs to be thought out quite carefully. Now, find this relationship. We've said there are going to be 4 equations. We've seen what those are: mass, momentum, energy, and state. And so that's quite difficult to solve simultaneously. Very highly nonlinear problem. So one way to solve this problem isn't to solve them all in one go, but being more systematic. And the reason we do this is that when we come to look at, say, lecture 6, and we're looking at flows where we're either changing the momentum because drag is imposed, or changing the energy because heat is added, then you'll see how this kind of approach maps onto that. So we have these 4 equations. So what you could do is you could solve 3 of the equations. You could solve mass, momentum, and state, and you could solve mass, energy, and state, and then you could combine them together, those 2 systems from A and B, to find the solution. And indeed, that's what we're going to do. So if you solve mass, momentum, and state, it's what we call a Rayleigh flow. It's when heat is added, so equation of energy is not conserved. When the equation of there's a change in the energy in the system, or you can solve mass, energy, and state, and this occurs when the momentum change occurs due to frictional forces. The algebra gets a bit heavy, and so my point isn't about the mathematical manipulation. That's pretty standard, straightforward. The point is to just focus on the end result, which is how we get the solution, conservation principles, and really what it means at the end of the day. So we can go through a series of algebraic steps by doing a manipulation on the momentum equation. And if we do that, we end up with the Rankine-Huguenot relationship between the density of the ratio of density after to before in terms of the strength of the shock. And this is quite interesting because we can now start to look at the case when the strength of the shock is very weak. P2 over P1 is a lot smaller, is about equal to 1. And what happens in this particular case is as the shock strength decreases, the strength of the shock is P2 over P1, which is actually 1 plus delta P over P1. It tends to be proportional to the density ratio, proportional to the change in density divided by rho 1. And this corresponds to the case where there are no energy losses and things change very quickly due to where the flow is isentropic. And this is going to be one of the approximations that we'll use later on when we come to look at some aspects of aerofoil theory. So when the shocks are very, very weak, the pressure change is proportional to the density change, with a coefficient of proportionality being the isentropic index. Throughout most of the course, apart from a couple of examples on CO2, we take it to be 1.4. So what we can do next is try to find, what we're aiming to do is find a relationship between, and a second relationship between P2 and P1, which we can get from the momentum equation combined with the equation of state. So we end up P2 over P1 being expressed in terms of the Mach numbers. And this gets our second relationship known as the Rayleigh line of rho 1 over rho 2 in terms of strength of the shock and the Mach number. Our second relationship, what we get from the continuity equation of state and conservation energy, is the Fano line, our second relationship between P2 and P1, expressed in terms of Mach number. And now we have our Rayleigh line and our Fano line, then the intersection will tell us the relationship between M1 and M2. So matching them together, we end up with this quite difficult algebraic equation that admits two very simple solutions. And the two solutions are that the Mach number doesn't change. And now that might in itself seem rather trivial, and that there is nothing there, but that is certainly not the case. You can end up with the Mach number unchanged, but with a particular flow feature present, like a sound wave, for instance. And so that doesn't mean that there is nothing there. It just means the Mach number upstream and downstream are the same. The second one is this relationship, more complicated relationship between M2 and M1. What this means is that if there is a solution where the Mach number upstream is, just write this down. So what this second thing is quite important. It says if M1 is less than 1, then M2 is bigger than 1, and M2, 1 is bigger than 1, M2 is less than 1. So in our kind of using our classification from before, if the flow is subsonic, it becomes supersonic. If it's supersonic, it becomes subsonic. We're going to see an additional constraint why one of those solutions can be dismissed. So the right-hand graph here just shows the intersection of the Fano line and Rayleigh line, and the jump between one state and another. Now, given we know M1 and M2, then we can find out the strength of the shock and the density ratio. Now, one of the constraints we need to kind of take into account is what happens with entropy. As we said before, entropy is the amount of heat added divided by dt, so dq over t, and it has a very important constraint that it can't decrease in time. And so this inequality will put a strong constraint on the type of solution that can be kind of admitted. So for an ideal gas, we can express the change in entropy in terms of change in temperature and change in pressure, and integrating across this change in state from 1 to 2, and we can get the change in entropy expressed in terms of temperature ratio and pressure ratio. Now, plotting this out in terms of the Mach number, which is just under the, we see that if M1 is bigger than 1, then the entropy increases. So that means these shocks are possible. This is a valid solution. If M1 is less than 1, it means the entropy decreases, and of course this is unphysical. So out of those two solutions that we can get, in terms of M1 being larger than smaller than 1, the only one that can be really admitted, the only one that is admittable, is the flow starts off as supersonic and then becomes subsonic. And that places an important constraint on the type of flow. This shows these two graphs show the variation of P versus rho and T versus S. We kind of use these quite a lot, these PV. This is a really P, 1 over V, and T versus S diagrams for looking at systems, Carnot cycle and the like that you back before. And this shows the two solutions from the Fano and Rayleigh lines plotted, and the intersection of both of these give rise to the two solutions. Those two solutions that we just discussed are the case with M1 equals M2. Again, that seems a trivial solution, but elicits something like a very weak shock wave. Very important when we look at expansion pans in lecture 3. And the other solution is the branch of supersonic flow becoming subsonic. And you can see these kind of two solutions. The two solution here would give an isentropic relationship because the entropy is isentropic because the entropy is the same before and afterwards. The other one is the entropy is clearly increased, demanding that the solution of subsonic to supersonic is rejected. Now this is quite important. So because this kind of table tells you kind of what happens with the key variables in terms of density, pressure, and velocity. So the first thing is that, and we need to make sure remember these, is that the Mach number afterwards is less than 1, so it's subsonic after the shock. Energy is conserved, so it means there's no change in stagnation temperature. This constraint of the stagnation temperature not changing is used almost throughout all of the analysis, apart from when we're looking at Rankine flows where we're adding heat. So this is pretty much a standard assumption. You can't measure stagnation temperature, but as we've discussed in the more fundamental aspects of fluid mechanics, it's an important concept and measure that's used in the calculations. The next one that we need to look at is the following, is that shocks cause the pressure to rise. The flow is essentially compressed and pressure goes up. The temperature increases across a shock, so things get hotter. And you can kind of have an intuitive sense that that's the case. The more complicated ones are whether what's happening to velocity being decreasing after the shock, and the reason why it's not that straightforward is because velocity is a bit more, it's less intuitive. Is the velocity essentially is the Mach number times speed of sound, which is gamma RT. So T goes up and then goes down. So on an intuitive sense, it's not that straightforward to see that the velocity in total goes down itself. Our intuitive sense of fluid mechanics is generally built around incompressible fluid mechanics. And so sometimes that intuition is lost a little bit. Okay.